Hello there, guys. I'm Shami, and welcome to AP Precalc. Today we're going to be going over Units 2.1 through Units 2.3. So our first unit is actually topic 2.1, and it's changes in arithmetic and geometric sequences. So there's two ways to find this, right? And those ways are recursive and explicit sequences. So what is an arithmetic or a geometric sequence, in fact? So an arithmetic sequence is a sequence that follows as is. So let's say if A, for example, let me just change that to, let's say, A1. And our A1 is equal to 1, just to keep it simple. And so the formula for the arithmetic sequence goes A1 is equal to A1 plus D. So this is how you would technically see if it were an arithmetic sequence. So let's say 1 is our A1, and so 1 plus, let's say D in this case is difference. In an arithmetic sequence, D refers to difference. So let's say our difference is 2. So that gives us 3. Sorry about that. 3. So our sequence would be as follows: 1, 3, 5, 7, and so forth. Yeah, sorry about the messy handwriting, guys. But that's how it would be as it follows. And in a geometric sequence, we'd be tasked with finding, let's just use 1 again as our A1. But instead, this time, we're actually be going to be using A1 times R, because a geometric sequence is, instead of adding like a normal arithmetic sequence, is actually multiplying, and it could be multiplying by any number. So in this case, let's just say it's 1 multiplied by 2. So that gives you 2. But instead of our arithmetic sequence, this is actually going to be using 2 and then multiplying it instead of adding it. So our first A1, as we know, is 1, then 2, then it becomes 4, because instead of 2, instead of 1, you replace it with 2. 2 times 2 is equal to 4. So that's where we get our 4. And that becomes 8, and so forth. But how do we find these dotted lines, right? These dotted lines represent the next numbers of the sequence. So how would we find them? So we have two ways to find them, and they're called explicit. I'll just shorten it because I can't write the whole thing correctly. So explicit and recursive. So our explicit and recursive parts are as follows. So it is going to be A. So this is A is equal to, and this is in an arithmetic standpoint. This is an arithmetic sequence. So A would be, according to the explicit formula, A is going to be used as a n plus d times n minus 1. So that's our arithmetic way sequence by using an explicit formula. So if we were to find for the next numbers of the arithmetic sequence, we would use this in an explicit way. But there's also the recursive formula. Both of these formulas will be actually used on your tests because teachers will like to see your grasp on the material on finding using an explicit and a recursive sequence. So, unlike the explicit formula, our recursive formula is actually going to be an and a n minus 1 plus d. So the difference between an explicit and recursive formula is that if you were to find the next few numbers of an arithmetic sequence, you would use the explicit formula. Since it is a is equal to an plus d times n minus 1, this n refers to the number of times that you completed the sequence. So technically you would start out with a of 0. This is what they would call it as ace, so ace of 0. And so you would say whatever number given to you as ace of 0 is d times n minus 1. So that number is 0. But in that case, you would think that, oh, well, it wouldn't work out. But actually, it would. It would actually just become 1. This total thing would just become 1. And if you were to try that on a geometric sequence, yeah, sorry about that messy handwriting, guys. Very hard writing here on a MacBook, right? So here on our explicit formula versus a recursive formula. So for a geometric sequence, an explicit formula would be ace is equal to ace of n times r to the power of n minus 1. So as we already know, guys, our geometric sequence is actually just like multiplication, right? So the sequence in itself uses the previous number found multiplied by r, which is our ratio, hence r. So r to the power of n minus 1. So let's say we're on our third term. Let's say ace is ace of 3. So we're on our third term. Then whatever this number is, let's say uh, it's like 10, right? Then we would multiply by the common ratio. Let's say in this case it was 2 times n minus 1. So our n, this thing is actually our 3. So 2 times 3 minus 1 is just 2 squared. So it would be 10 times 2 squared. That would give you 40. 40. Continuing on. Oh yeah, I forgot about the recursive sequence. So our recursive sequence for a geometric, a recursive formula, in fact, in terms of a geometric sequence is going to be, as you know, you might have already guessed, but it's actually going to be a is equal a n actually. A n is equal to a n minus 1 times r. So this is just like a basic outline of what your geometric formula truly is. But then when we actually use, we're actually going to use explicit formulas to find the answer. To find the answer. Yeah, it's a little shabby, guys, but I think you're getting the clear message here. That's it for topic 2.1. So if you want to stop and take a break and maybe think about all the things that you've learned, I think this would be a great time. But moving on, we're going to move into 2.2, change in linear and exponential functions. So don't panic, guys. Exponential functions are supposed to be hard. So basically what topic 2.2, change in linear and exponential functions, is basically that if, let me draw this diagram. Let's say our so if we use these things called output input tables, and that's what this necessarily is. It's just a poorly drawn input output table, and our input is going to be x, and our output is going to be f of x. So technically what we're saying is that for a value or a function to be considered a linear function, its output values, which is the x here, oh wait, sorry, the input values, actually the input values and the output values are right here. So for a function to be considered linear, over equal length input values, the output value must be increasing at a constant rate. Like I'm going to show you after I've created this table. Is that, so let's say our x is 2, 4, 6, and 8. So if this were a linear function, then you would see these are equal length input values, correct? Then we would see a constant increase in the output values. So in these output values, there's a constant increase of 4 in every one of these. So like 8 minus 4, like all of you know, is 4. So our output intervals are distributed by 4. But if this were an exponential function, which is modeled by using that our input over equal length input values, the output values must change proportionally. So I'll show you what that means in a sec. So our input value, as we know, is x. Our output value is actually f of x. So let's use our previous example, say 2, 4, 6, 8, correct? But this time we're going to be using it as, and we're going to model it as an exponential function. So this is going to change proportionally. So this unfortunately does not change like a linear thing. If you were to graph this, you would probably see something like this. And this is what your exponential curve is meant to look like. it's supposed to look like this. It's supposed to be rising in that direction. So if you I know that you're smart enough to know this, you would be noticing that our x value is actually squared each time it undergoes this function. So 2 squared, 4, 4 squared, 16, 6 squared, 36, 8 squared, 64. So that is how change in linear and exponential functions are modeled. And so for our exponential function, it's usually going to be modeled in some accord to this. It's going to be a times b of x. That is what a basic exponential function is going to be looking like. So next part is actually identifying them, identifying a linear and an exponential, function based on their characteristics. So an exponential function, basically it's supposed to look like this. A linear function would have a normal slope intercept formula. Should look like this. An intercept, so this would be our slope, this would be our x, and then this is our b value. And this is our slope intercept formula used to find for a linear equation. So that is one of the characteristics. And another part for why we were talking about arithmetic and geometric sequences in 2.1 was that when we jumped to 2.2, we learned that these sequences are actually implemented. Like this exponential function is technically just a geometric sequence, and our y is equal to mx plus b, or our linear function, is actually just an arithmetic function. That is why it is necessary for us to learn and comprehend how to identify and use geometric and arithmetic sequences. And then we move on to topic 2.3. So topic 2.3 is necessarily the broad thing of actually identifying and understanding exponential functions. So we're going to be talking about the identification of what it means to be an exponential function. So necessarily, like we were talking about, an exponential function is a times b to the power of x, correct? So that's our basic formula. That's how we identify that a function is exponential, and it will be in some way or form of a times bx. And so this exponential function can be written in multiple ways. So it could be written as 2 times 2 to the power of x. Yeah, this is just very simple, but it could be written this way. But what if it is written as 2 times 2 to the x minus 1? Well, this is technically transforming this graph into this function into this, which you will need to maybe graph on the test. So what does this x minus 1 technically mean? So it would just be this negative 1 is just translating the graph of 2. One of my favorite things about exponential functions is the natural base of e, actually. So the natural base of e is one of my favorite topics in exponential functions. And natural base of e is actually defined by limit of x to infinity by 1 plus 1 over x to the power of x. I don't think you technically need to know this, but these are just like the definitions to help you understand. So E is roughly 2.718, and there's a bunch of numbers over, but it's roughly 2.72. But you don't really need to know that because if you are using a calculator, it's most likely going to just be E. And if you're not allowed to use a calculator, such as your AP test, there's a section where you cannot use your calculator, it's fine because this E will actually be used as natural log in our log functions on the next topics. So what will we be using E for in exponential functions? So E is, well, it can be rewritten in our A is equal to A times B of X formula by just saying A times E to the power of K X. So in this, K is necessarily just a constant number, a constant real number, so it can just stay that way. So it is fine to write it that way. And when we know that A is greater than 0 and K is also greater than 0, we can confirm that this is a exponential growth function. So this will be used to model things such as population or interest or many other things. Usually population, but this is our growth function when A is greater than 0 and K is greater than 0. But when A is greater than 0 but K is less than 0, that immediately defines K, well, the whole function, as a decay function, since the value is in the negative, so it will necessarily become negative kx. So let's talk about how we could probably transform an exponential natural base function. So if we were to write e to the power of 2 of x, that necessarily, this is a horizontal shrink by 2. So the graph would be like this, and it would just be shrunk to this. That is what e to the power of 2 of x does. And if we were to write e to the power of negative x, as we already known from doing the previous one, where it was 2 times 2 to the negative x, we can easily find that this is just reflecting our graph across the y-axis. So if it were like this, it would just be reflected like this. I should probably write that in a different color, so sorry, I'll redo the problem. E to the power of 2 of x will give you this graph, correct? Then we use this, and it, sorry, that was a mistake. E to the power of 2 of x, then you just wait. E to the power of negative 2x, then you just flip it that way. You flip it across the y-axis. Sorry guys, got a little confused there. But I hope we're getting a hold of this topic. And the next part is actually the one that we did somewhere. So e of x times 2. So this will just vertically stretch the graph of e by a factor of 2. So I would just vertically stretch it. And then this is just like I was saying, this whole thing is about growth and decay functions. Moving on, then we could model a growth function using c over 1 plus a times b x. That would be our logistic growth function. And our c is actually a limit to the growth. So if we were to write this as 20 over 1 plus 3 times e of x, then our limit is 20. So we cannot, our graph will, it won't go past this point, which is 20. So our graph is a limit to this. So we will draw our limit as x approaches infinity. Our limit is bound to 20. And then moving on, that would be the same if you were to write it as a decay function, which is also c plus a times b to the negative x. So that would apply to a decay function as well. So moving on to, well, graphing this exponential functions as logistic growth and logistic decay functions is actually very easy. You just plug it into your calculator. But what if you don't have a calculator? Then what would you do? So let's take this example. So 8 over 1 plus 3 times 0.7x. Yeah, it's a weird b value, but if it works, it works. So how will we graph this? First, we have to find, well, the y-intercept, right? So usually on tests and quizzes, they will ask you to find y-intercepts, giving you a logistic growth function. So to find the y-intercept, it would just be technically f of 0, because this is our function. And if we just replace our x with 0, we would get what our y-intercept is, which would technically just be 8 times 1 plus 3, because 0.7, so anything to the power of 0, as we know, just becomes 1. So it's 1 plus 3. Then our y value we know is 2. And they would also ask you to find horizontal asymptotes. Horizontal asymptotes would be like y is equal to 0 and the limit to the growth, which is y is equal to 8. So this example shows us how we could find horizontal asymptotes and our y-intercept. But you would actually not just normally use these, right? You would actually have to like use it in a problem. So it would give you such problems to find how to model like cities or places population. So it's kind of a little hard to actually do that because you would be going with this percent decay thing known as R is equal to B minus 1. So this B value is what you would get from trying to find how to model a population. It may seem a little confusing from what I'm saying because when I'm talking it's very confusing, but if you were to see it, then it would kind of look like this. Like if in 1980 the population of Phoenix, Arizona was 200,000, right? 200,000. And in 1985, it rose to 500,600. Well, let's actually make it a little bit more difficult, shall we? And by that, I mean I will actually get rid of this even number thing that we have here, these two, that they're too easy now. So 2,000, 200,000, 273,000 in 1980. The split line is to indicate that this is separate and this is separate. 532,600. So how you would find B is you you have this equation, right? But then you also have the original equation for modeling an exponential function, which is a times b to the x. And that would give you 273,000 times something to the power of x. So we need to find b. So we need to find like what this is so that we could actually model this. So it's pretty simple. Put b and then put, you put the numbers to the root of 5. This is a 5-year difference, so 532,600 over 273. Sorry guys, it's very slow to write through all of this. So now you would have to calculate that. So I think you guys should take a minute to calculate that. So I've calculated it, and I hope that you guys have as well. It's 1.143. It doesn't have to be in this in exactly 3 decimal points unless it specifies. If it says round to the tenths, round to the hundreds, round to the 10,000s, stuff like that. But I basically just do this. So our function's value becomes 1.143 to the power of x. So if we were to graph it, then we would know that our starting point is 1980, and every year that goes on after that, we would just need to add it to 1980, and then you would find that let's say this is 5, then 5, then we would be, then our intersection would be at 532,600. And that's a pretty cool thing. But going back to our formula, so it may seem that I've erased everything, but then I still do remember. So our R is equal to B minus 1. This is once again to reaffirm that this is actually a decay or a logistic growth function. So our B value was 1.143 minus 1. That gets you your R value of 0.143, but this is not the percent increase. Actually, you would actually have to multiply that by 100% to find out that the population increased by 14.3% every year. That's R. And this could be modeled, well, it doesn't have to be B of X, it could be E, and you could easily find it. But there will be other questions that require you, like, let's say, for example, 1,265,300. This is just some random number of, let's say, New York in 1921. Then our bottom, so our denominator, like 52.13 times e to the power negative 0.0311x. So they would necessarily want you to graph this, and they would want you to say, well, in what point could this city well reach 750,000? So then you will look at the graph and you go, well, 750,000 is here. And then this here, then you would identify it with this phi value, and then you would add it to whatever date this is. Let's say, like I was saying, 1921. Let's say 33. Then you could say that this was in 1944. And that's it for topic 2.3.